Okay, so I left off last lecture with this example, and I mentioned that we can use the properties of the natural logarithm, in particular how it behaves with products, with exponentials, and with quotients, to try and help us deal with a derivative of something very algebraically complicated like what we have here. So we've seen examples like this a few times already in class, and essentially what we're going to do is we're going to start off and let y be equal to the thing that we're trying to differentiate. Alright, and the main idea here is that we can now, now that we've given this thing a name, we called it y, we can now take the natural log of both sides because we know these three rules, right? We have these three rules in our back pocket, and we know that they're really going to help us take this thing apart into much simpler pieces that we can then deal with, right? So we take the natural log of y, well, that's going to be equal to the natural log of this whole thing. Right? And now we just sort of want to peel back the layers of what's going on here, right? So the first thing that we want to do to try and algebraically simplify this right-hand side is to recognize that the outermost problem that we're up against is the fact that this thing is a quotient, right? So we want to use this third property for natural logs to go ahead and turn this quotient into subtraction. So I've got the natural log of my numerator, and I'm going to subtract the natural log of my denominator. Okay. Now, we've all got that in our notes already, and you can just go back to it earlier in the video if you need it. It's all here for that. And now what we want to do is, to make this even simpler, we now recognize that inside of each of the two logarithms that we have multiplication. And so we can use this product property for the natural logarithm to go ahead and, if I bring this up here, we can take both of these natural logs apart one step further. We can say that this is the natural log of x plus 1 to the 11th e to the x. I said we're going to use the product property. We should probably actually use it. So I've got the natural log of x plus 1 to the 11th plus the natural log of e to the x squared. Right, that's what happens to this first natural log. Now I've got subtraction, and I'm going to use my product property for the natural log on this one as well. But I have to be a little bit careful, right? I have to make sure that this minus sign actually hits both terms. So I'm just going to put parentheses around what I'm about to do. Now I've got the natural log of the square root of x to the 8th minus 1 plus, and remember this is inside the parentheses, plus the natural log of x to the 3/2 plus 10, all raised to the 1/8 power, and close the parentheses. Okay, now, you can see that already each one of these four pieces is simpler than if we had just tried to attack this entire thing all at once. But we can actually still make it a little bit simpler, right? Each one of the things inside the parentheses here, right, each one of the things inside of a natural logarithm right now is something raised to a power. And so we can actually use this, what I have listed here is the second property of natural logs, to go ahead and take down the exponents as multiplication. All right, so let me get rid of our definition of y. And so what we can say now, here I've got x plus 1, the whole quantity, raised to the 11th power. So that's going to be 11 times the natural log of x plus 1. Now here, I've got x squared as my power. I can bring that down in front. And quick side note, natural log of e simplifies. Right, this is actually something, it's a number we know and love. I'll leave it to you to go ahead and simplify that. Right, and then we've got, right, inside our minus sign here, inside the parentheses attached to the minus sign, that is, we've got the natural log of the square root of x to the 8th minus 1. And so what we want to recognize here is that this square root is really the same thing as a 1/2 power. And so we can bring a 1/2 out, multiply by the natural log of x to the 8th minus 1. And lastly, we've got a 1/8 power here, which can hop out in front. So we have this, right? We've used all three properties of our logarithm. We've used the quotient property, right? So what happens when you've got division inside of a natural log. We've used the multiplication property to separate each part out as addition. And now we've recognized that we've got some powers. In fact, we have a distinct power in each one. And so we've used the what happens when we've got exponentiation inside of a natural logarithm. Or really any logarithm, but it just happens to be the natural log in this case. And so we've broken this apart into 4 distinct pieces. And what I want you to recognize now is that each one of these pieces is relatively easy to differentiate, right? For instance, the natural log of x plus 1, we're going to have to use the chain rule, but it's a heck of a lot nicer than having to use the quotient rule, and then inside the quotient rule we had to use the product rule twice, and inside of each of those product rules we had to use the chain rule 2 times each. Right? So this is definitely much nicer than trying to tackle the original problem as it was stated. So the last thing I want to mention about this, and I'll leave the rest as an exercise, the last thing I want to mention is that I've got this formula right here, and if I just remember what was on the original left-hand side of the equality here, this was the natural log of what we called y. Right, so the last step here is to recognize that what we really want, right, because we let y equal the thing that we really cared about at the beginning, and we were asked to find the derivative with respect to x of that thing, the thing that we really care about here is y prime, or dy over dx, right, whichever notation you're more comfortable with. And so what we have to do now is really recognize that by taking the natural log of both sides, we've changed this from just a straightforward differentiation problem into one of implicit differentiation, or really just the fancy chain rule, right? So we've got this equation for the natural log of y, and y is the thing that we care about. So what we're going to do in order to get a y prime out of this is differentiate both sides. All right, so I'm going to leave the derivative of the natural log stuff that we just figured out here. I'm going to leave that as an exercise. I just want to remind you of what's going to happen to the natural log of y term. Right, so we take the derivative with respect to x of the natural log of y. And because of the way we defined y is really a function of x. And so this makes sense to consider. Right, and so this is really implicit differentiation if you want to think of it that way, or it's just an application of the chain rule. Why is that the case? Well, y is a function of x, and it is stuck inside of another function, in particular the natural log. So what we're going to have here is the derivative of our inside function with respect to x, that's just dy over dx, or y prime, whatever you want to call it, multiplied by the derivative of the outside function, which in this case is the natural logarithm. We take the derivative of the natural log, that's going to give us 1 over whatever was inside it, because this is really just an application of the chain rule. So this is going to be 1 over y. Now, we've got this as the derivative of the natural log of y. You'll find the derivative of these 4 pieces as an exercise. And then it's just a matter of putting all the pieces together to get one final answer for the derivative of y that only depends on x. And again, I'll leave that to you.